What are some of the real-world applications that can benefit from long-context language models, according to the paper?
According to the paper, some of the real-world applications that can benefit from long-context language models include long document question answering, multi-document summarization, long-horizon agent tasks, and repo-level code understanding. These applications require the models to process and understand extensive amounts of information within a long context window, ranging from 32K to 2M tokens. Additionally, the paper mentions that long context models can be utilized for tasks such as passkey retrieval, needle-in-a-haystack tasks, and long document question-answer or summarization over Casper. These applications demonstrate the need for large language models to effectively handle and reason over entire input sequences, showcasing the practical implications of long context understanding in various domains.
Can you explain the difference between alibi and rope embedding in the context of training transformers with short sequences and applying them to longer sequences during inference?
Alibi and rope embedding are two different approaches used in training transformers with short sequences and subsequently applying them to longer sequences during inference. Alibi is based on the idea of using a fixed-size embedding for each token in the sequence, allowing the model to process short sequences efficiently. On the other hand, rope embedding stands for relative positional encoding, which introduces relative positional information between tokens in the sequence, enabling the model to understand the relationships between tokens even in longer sequences. Alibi embedding focuses on creating embeddings for tokens in the sequence without considering their relative positions explicitly. This approach is beneficial for training transformers with short sequences, as it simplifies the embedding process and allows for faster computation. In contrast, rope embedding adds relative positional information to the token embeddings, which is crucial for understanding the context and relationships between tokens in longer sequences. By incorporating relative positional encoding, rope embedding helps the model handle longer sequences more effectively during both training and inference stages. In summary, alibi embedding provides fixed-size embeddings for tokens in the sequence without considering relative positions, making it suitable for processing short sequences efficiently. On the other hand, rope embedding introduces relative positional information to token embeddings, aiding in understanding token relationships in longer sequences, thus enhancing the model's performance when dealing with extended contexts during inference.
How does the paper propose to evaluate long-context LLMs differently from traditional evaluation metrics like language model perplexity and passkey retrieval?
The paper proposes to evaluate long-context LLMs differently from traditional evaluation metrics like language model perplexity and passkey retrieval by introducing a new evaluation method called in-context learning, ICL, on extreme label classification tasks. This approach requires LLMs to scan over the entire input to understand the label space, necessitating the models to comprehend the entire input to make predictions. The paper emphasizes that traditional metrics, such as language model perplexity and passkey retrieval, do not adequately measure LLM's ability to comprehend and reason over the entire input sequence. The proposed ICL task involves recognizing fine-grained differences among an extensive label space based on extensive context, which serves as a natural testbed for assessing long-context understanding. Additionally, the paper introduces the LongICLBench benchmark, consisting of 6 carefully selected tasks with varying difficulty levels in terms of context length and label space, to systematically assess how extended input capabilities impact model performance in fine-grained text classification. This novel evaluation method provides a more comprehensive and realistic assessment of LLM's long-context understanding capabilities compared to traditional evaluation metrics.
What is the main motivation behind proposing in-context learning, ICL, on extreme label classification tasks in this paper?
The main motivation behind proposing in-context learning, ICL, on extreme label classification tasks in this paper is to evaluate the ability of long-context large language models, LLMs, to comprehend and reason over the entire input sequence. Unlike traditional evaluation metrics like language model perplexity or passkey retrieval, which do not fully capture the LLM's capacity to deal with realistic long-sequence tasks, the authors aim to assess the model's performance in recognizing fine-grained differences among a vast label space based on extensive context. By introducing ICL on extreme label classification tasks, where each example demonstration could span thousands of tokens, the paper seeks to provide a more challenging and comprehensive testbed for evaluating the long in-context learning capabilities of LLMs. The goal is to understand how these extended input capabilities impact model performance in fine-grained text classification tasks, and to gain insights for improving the design of long-context LLMs.
Can you describe the LongICLBench benchmark and its significance in evaluating long in-context learning tasks for large language models?
The LongICLBench benchmark is a collection of 6 carefully selected tasks with varying levels of difficulty in terms of context length and label space. These tasks are designed to evaluate long in-context learning for large language models. Each task consists of datasets from different domains such as banking intent detection, relation extraction, dialogue-based relation extraction, and fine-grained label classification. The datasets range from short to long context lengths, with varying numbers of unique labels. The benchmark ensures a balanced distribution of instances from each class to reduce bias. The significance of LongICLBench lies in its ability to provide a comprehensive evaluation of long in-context learning tasks for large language models. It offers a testing scenario where models are required to comprehend extensive context to make precise predictions among a vast label space. By assessing the performance of models on tasks with increasing complexity, LongICLBench reveals how well LLMs can handle tasks that demand understanding and reasoning over long input sequences. The benchmark helps researchers and developers gain insights into the strengths and weaknesses of different long-context LLMs, guiding improvements in model design and performance for real-world applications.
What are some of the strategies mentioned in the paper to address the computational challenges faced by transformer-based models in handling long context inputs?
Some of the strategies mentioned in the paper to address the computational challenges faced by transformer-based models in handling long context inputs include continued fine-tuning of the LLM with longer context inputs to adapt the model to extended sequences. Additionally, techniques such as position extrapolation and interpolation, leveraging relative rotary positional embedding, are employed to extend input length beyond the training phase. Other approaches involve sliding memory window and chunk segmentation methods to mitigate computational issues. Furthermore, alternative architectures like selective state spaces models, a variation of recurrent neural networks, are explored to handle long inputs more naturally and efficiently. These strategies aim to enhance the capabilities of LLMs in processing long context inputs effectively.
How do the experimental results in the paper compare the performance of transformer-based models with RNN-based models in extreme label classification tasks?
The experimental results in the paper show that transformer-based models consistently outperform RNN-based models in extreme label classification tasks. Specifically, the evaluation conducted on a series of recent open-source long-context language models, including models like Gemini and GPT-4 Turbo, revealed that transformer-based architectures generally exhibit better performance across all evaluated datasets compared to RNN-based architectures. The results indicate that transformer-based models, despite falling behind powerful API-based models like GPT-4 Turbo, demonstrate more robust performance in handling extreme label classification tasks. The experiments showcase that for tasks varying in complexity levels, from relatively simple tasks like Banking 77 to more challenging tasks like TACRED, Dialogue RE, and Discovery, transformer-based models consistently outperformed RNN-based models. Additionally, the The study highlighted that while most transformer-based models benefited from extensive context and more demonstrations, RNN-based models struggled to match the performance levels achieved by transformer-based models, especially in tasks requiring long context comprehension. Overall, the experimental findings underscore the superior performance of transformer-based models over RNN-based models in extreme label classification tasks, emphasizing the effectiveness of transformer architectures in processing long context inputs efficiently.
What is the observation regarding the performance of models like Qwen and Mistral in relation to the demonstration length in extreme label ICL tasks, according to the paper?
The observation regarding the performance of models like Qwen and Mistral in relation to the demonstration length in extreme label in-context learning, ICL tasks, as per the paper, is that their performance is almost linear with respect to the demonstration length. This means that as the demonstration length increases, the performance of these models in extreme label ICL tasks follows a linear trend. Specifically, the paper notes that the performance of Qwen and Mistral shows a consistent linear relationship with the length of the demonstrations provided. This observation suggests that there might be an underlying mathematical relation between the performance of these models and the complexity of the task in extreme label ICL scenarios.
What is the lost-in-the-middle phenomenon mentioned in the paper, and how does it relate to the position distribution of instances in long in-context learning tasks?
The lost-in-the-middle phenomenon refers to a situation where certain models exhibit a decline in performance when instances of the same class are grouped together in the prompt during long in-context learning tasks. This phenomenon is related to the position distribution of instances in these tasks because the positioning of instances within the prompt can significantly impact the model's ability to accurately classify and differentiate between labels. When instances with the same label are scattered throughout the prompt, some models, like intern LM2-7B base, show acceptable performance regardless of the instance placements. However, when instances of the same class are grouped together in the prompt, there is a general decline in performance across most models. Models such as Mistral 7BV0, 2 base and intern LM2-7B base experience significant performance drops when instances are grouped, indicating a sensitivity to instance grouping. The position distribution of instances, whether scattered or grouped, plays a crucial role in influencing how models handle and classify labels within long in-context learning tasks, showcasing the impact of instance positioning on model performance.
Can you explain the difference in model performance between scattered and grouped distribution of instances in extreme label classification tasks as discussed in the paper?
The paper discusses the difference in model performance between scattered and grouped distribution of instances in extreme label classification tasks. In the scattered distribution scenario, where instances with the same labels are randomly distributed within the prompt, certain models like intern LM2-7B base show acceptable performances, achieving around 60% accuracy on specific labels regardless of instance placements. Conversely, models like ChatGLM 3-6B32K exhibit consistent performance across a wide range of labels. Notably, the GPT-4 Turbo model consistently surpasses an 80% accuracy threshold for most label types in the scattered distribution setup. On the other hand, in the grouped distribution setup where instances of the same class are placed adjacent to each other within the prompt, there is a general decline in performance across most models. Models such as Mistral 7BV0, 2 base and intern LM2-7B base experience significant performance drops, indicating a sensitivity to instance grouping. The analysis reveals that intern LM2-7B base performs well only when instances with labels are positioned at the end of the prompt, while models like ChatGLM 3-6B32K demonstrate resilience to changes in instance positioning, maintaining high performance across various positions. Surprisingly, even the high-performing GPT-4 Turbo experiences a notable decline in performance by 23% in the grouped distribution scenario, indicating challenges posed by group distributions on model performance.